would go back to old technologies that you know, or trying to think how to use the situations that I have and come out with some new ways to build diodes and transistors and things like that on these materials. So the fact that we have a gap, that is the main features that enables us to use all this, these technologies in order to create electronic devices, and that's why it's called semiconductor industry, because all of it is built that we have a gap in our system. Now, in this case, we put in impurities that are acceptors in one side, and now I'm just repeating things that we did in the previous lecture. And we put here something that is donor. Acceptor means that it's missing one electron in its valence and in the atomic valence band, which means that basically it wants to get an electron from somewhere, and donors have 5 electrons in their external band, meaning that they want to get rid of one. And if we didn't have this junction, the situation would have been very simple. These guys with temperature, with light, with whatever energy source exists would move from here to here. And that's a situation which we discussed. The same here. Here, in this case, electron will move from here to here and create holes in the valence band, again opening the possibility of conducting electricity. Yes. Here we have a very strange situation. Basically, these additional electrons that would have moved here look to their left and say, hey, there's much better states, much lower in energy on your left. Why go up here? We'll move into these states.
How would they actually, wait, just before, how would they actually move from the donor band to the conductance band? Where would they get that energy to jump? Because they can't gain another electron. Where would they gain it from? So what is that jumping?
What is this jumping? Okay, I'll be more specific. Okay, I just didn't want, I'm using a continuous line here not to be confused between electrons and, okay, to move from here to here you need, let's call the lowest point in the band EC, EV. You need E minus ED, right?
Mm-hmm.
So your question is, from where is this energy?
Yeah, why would they just magically get the energy?
So, first of all, let's ask in general, from where does any system on our world get energy?
Somewhere else.
Right. And there are 2 very clear sources of energy that are around. One is, I don't know if you noticed, you're living in an environment that has much more energy than 0-point energy, right?
Big thermal energy?
Right. You live in a place where you're surrounded by air molecules that hit you and so on and so forth. So it's thermal energy. So you have a source which is KB KBT. And since this difference of energy is usually much smaller than KBT, so you have an available energy source which allows you to create holes in the donor band and moves them to the conductance band. So that's the most abundant source. The other source is actually the source that you are using in order to exist. Well, you are using a lot of energy as a human being, as any living system. So from where does that energy come? You are not getting it from the environment, because in simple terms, you need free energy, energies that can perform work, and the thermal energy around you is not available for doing work. So from where do you exist? So I assume, I've never seen it, but I assume that you eat sometimes. And if you go through the whole chain, anything that you eat here comes out of plants that have performed photosynthesis. Somehow captured photons and stored that energy into some chemical compound, into organic molecules that your body specialized in taking apart and pulling out energy out of it.
So it's from so it's like spray photons.
So it's photons, and actually semiconductors can use straight photons in order to create current, even, and we'll talk about it after we talk about a diode, because it needs two steps. One step is immediately obvious. Shine light on the semiconductor and you'll pull out an electron as long as h bar omega is much larger than EC minus ED. You moved an electron into the conductance band. So why do I say we need some more explanations? Because if this is the only thing that happens, wait a bit, and this electron will fall back, release a phonon, release energy, and all you did is made your semiconductor more hotter. That's not useful energy. You don't need even technology. Put a brick outside in the sun and it will become hotter. It's still not it's
Put
still...
a metal outside, it will also get hotter. Put a metal outside, it will also get hotter.
Exactly. It just gets energy. In order to get useful energy, you need to have a temperature difference. Okay, that's why your hot water sun collector gets cold water from outside, exchanges the heat from the solar panel, and sends it back again. If you don't have this temperature difference, you won't extract energy. So in this case, you need either to couple it with a cold environment so it will heat the cold environment and you can perform some work out of it, or use a trick to directly create current, which we'll talk later on. So basically, these are the sources of energy that enable you to create electrons in the conduction band. But here, in this process, you don't need energy. Actually, you gain energy. If I'm taking an electron from here to here, I'm leaving behind a hole. So let's look at some donors stacked here. It moves an electron to here. Okay. And leaves a hole here. Next one. So on and so forth until we get some area which we called dP, which is full of additional electrons. The area here which is full with additional holes to the point of dN. And we calculated it in the previous lecture. I'll just write it down here, since we'll need it in the following. So we have dN And we did another thing, we just calculated phi in this region, the electric potential. Why is there an electric potential? Just because you separate negative and positive charges, costs you energy. So this basically stops the process. Otherwise, all the donors on this side would become ionized and send it to all these acceptors here. It can't continue on and on, because as you fill up more acceptors and empty more donors, the distance between them grows. And the distance grows, the potential energy grows. It pulls them apart on a longer distance. So it stops somewhere, and therefore that was the rationale behind getting some regions, some finite length which has this charge, and beyond that it's back to normal. Because it can't already gain energy from moving to here because you gain energy because you're ED minus EA, but you lose potential energy. And it ends up. Okay, so if you have charge, you have potential. So we decided to define some potential at infinity. Pay attention that those distances don't have to be the same. It depends on the number of acceptors and the number of donors. If they're equal, so it's equal, but doesn't have to be. And we have here some phi infinity. And we got some form of the potential here, which we have written in the previous. Sometimes people prefer not to use the phi in infinity, but define here phi at 0 equals 0. That's how I have drawn it. And then the potential in minus infinity would be phi 0 all this we actually did in the previous lecture. Okay, so the important thing in the game here is that if we look what happens from left to right, we get some difference in potential between the left side and the right side, which will just denote as delta phi 0. Good. Now, what do we do in any electric circuit that we build?
Charge the person you charge it after. Create a voltage difference between the ends.
Exactly. Any electric circuit that you have ever built is based on the fact that you put a potential between 2 points. Usually it's your battery that connects one point around the circuit to the other. What is it doing there? Of course, pushing current, but you can also look on it as creating a potential difference between 2 points. Okay, so this thing exists naturally. Now you come and stick your diode into some kind of exactly as if you would have sticking a resistor. You stick your diode into some circuit and put a potential V here. If it would have been a resistor, you would go to Ohm's law and tell me how much current goes through the system. Fortunately, this is not a resistor. Well, it could have resistance, and it's non-linear, and Ohm's law is not relevant. And what we want to do in this lecture is understand how does the current respond to the voltage, meaning we put a voltage V. What is the current that we'll see through this circuit? Now, And if this would have been a resistor, where would the voltage fall on? Where would it have an influence?
Falls on between the ends of the resistor.
On the resistor. Here it will also fall on the PN junction or the diode. Now, where will it fall in the diode? Here it's a constant potential, it will just change it by a constant. The same here. The only place that it can have influence is here, in this region. So, if, and I'll use two colors here to, if I put up the voltage so it becomes larger, meaning delta phi 0, which is a situation with no voltage on the system, we put more voltage. Will just become a higher barrier. It will change a bit, a bit better. It will actually make it dp a bit smaller because it makes it harder to move a charge from side to side. But at the moment, let's not worry about this correction. If I put here on the other direction, we'll make it smaller, and the difference will become smaller. Okay. What does it have to do with current? Okay, to understand from where current can come into the game, I should actually look on these diagrams of the potential. Let's say I have somehow a hole was created here. How was it created? Perhaps an electron jumped into the conduction band because of heat, because of a photon, because of heaven knows what. Okay, what does it see? Excuse me, a hole created here. Remember, in electrostatics, positive charge, when it sees potential which is high here and low here, what will it do?
Low.
It will just move to the lower potential. So this guy will just be pushed by the potential difference to the left of the sample, and that creates a current.
Even when it's
We'll do balancing in a moment.
no, just because like the whole idea was that it can't.
Hmm?
What does it mean as a positive charge there? What you have is that the atom that was there has less electrons around it, right?
Right,
Because one of its electrons jumped to the next
well,
level.
it's what happens here. An electron jumps to a higher level.
Yeah.
It's missing an electron. It's a hole.
Yes,
it's a positive.
the atom becomes ionized.
Yeah, and this charge would like to go to lower potential because positive charge is pushed by potential.
The entire ion moves.
No.
So what does move?
Okay, this is actually a nice kids game. I don't know how many of you, there used to be these kinds of squares filled with numbers to between 1 and 15. Had 1, 2, 3, and so on and so forth, and one empty placer. And the game was to get all kinds of arrangements by moving things along. You can move any field case, but you can move it only into the hole, right?
Mm-hmm.
Now, you can describe what's happening here by moving of these tiles, but you can also describe it by moving a hole. You look from far away, what do you see? A hole that does some diffusion in this situation. The same thing here. Let's think on the simple situation where you have just a one-dimensional array. And here you suddenly have a hole, right? You're missing an electron. All of these guys are filled.
I see.
This guy moves to here, then you have a hole here. This guy moves to here, you have your hole here. So instead of telling your story as, I move an electron from one,
You say
I say the hole propagates on the other side. That's the meaning of hole.
I think I understand it.
And actually, do you know who's the first guy who and in what connection came up with this picture?
Neumann?
Hmm?
Neumann?
Dirac. A positron, which is the antiparticle of an electron, for him was a state where an electron left a band which was full of electrons. Think, you always have an electron positron creation if you start with, let's say, pure energy. What's the explanation? Same explanation like here. You had a filled band of electrons, one of them jumped up, and if you're looking from outside, you see one electron and one positron, a pair creation. And why don't you see the whole sea of filled electron states? For the same ideas that stands behind the solid state, that these are full bands, they can't do anything, so they are there, but you can't do anything to see them. Only if you put in a lot of electron and pull one of them above the gap, then you see an electron hole pair. Not in our material, but interesting general physics, and there's a lot of popular literature that you can read and at least now understand some of the concepts behind it. Okay, so since this is already in the field of engineering, everything here has names, so I'll give the name just for, so if you run into it, you'll understand what it means. So, holes from N to P, which is a process that I described here, is called and you have to understand these terms came out in the 30s and 40s when people started to research seriously semiconductor. And why it's called a generation current? Because this hole was generated, appeared here. It's not holes that you had to put in from the beginning. It was created by thermal energy or photon. And once it was generated, it creates current. Now, let's say we have a hole created on the left side. Well, you would say, basically, why do I care about it? Of course, it's sitting on the lowest potential, and it wouldn't want to climb back. But let's give it also a name. And this guy is at a hole from P to N is called Raycom recombination current. Why?
What current is created? Yeah.
Basically, if I have here a hole, in principle I could have a negative current coming, a negative electron or a negative charge coming down here and filling it up, so you would have some kind of current. Now, this, if you think about it, it's exponentially, the probability of such a current is exponentially smaller because it has to climb above this barrier. Okay, so you can stop me and tell me, excuse me, why are you bothering about this current? This is important. This is, of course, the charge will move from left to right. Whole charge. This won't happen, right? But let's stop a minute and think about it. So, we argued that this current is very small. What's the exponential barrier that I... But if such a current all the time exists, right? So charge will all the time move from here to here. And we won't have a steady state, and this region will become more... We are getting here a behavior that's not steady state. So we have to see that G generation is equal to, because otherwise we're not in steady state. So, without knowing anything about these two currents, I can write down because at the point, let's look, v equals 0, this equations no volt. You can look at it and say, I don't understand something. Phi here clearly pushes you from left to right and clearly strongly opposes you moving from left to right. So how comes the two currents are the same?
Yeah, I was going to ask why. Why would he say that?
First of all, I know that it must be true, because if I have current even without voltage, charge will move and the occupation will change. Right? Because when I'm looking only on phi, I'm forgetting one important thing. There's also a difference in the available energy states. The behavior of the particles, of the charges, is not only dependent on the potential, depends also on this difference. That's how we created it. So the fact that if I'm only looking on the potential, I see this behavior, I forgot all the loss or gain of energy because of the states.
So what you're saying is that it'll have this.
It will have potential. electrostatics is not the only factor in this game.
Electrodynamics?
No, it's just you have also another source of energy, which is the gap energy. So if I'm taking a hole from here to here, so I'm filling up so from point of view of potential, I gain energy, right? Because I'm going down the potential barrier, right? But if I take a hole from here to here, it means that I empty an electron out of here, and it has to move to a higher energy.
You have less electrons there because they jumped to the
So
to the acceptor band. So now you have less electrons. But
no, I'm moving a hole. I removed an electron from the acceptor band.
Moving from the acceptor to the donor band.
I'm talking about.
No, moving from the donor band to the acceptor band.
I'm taking a hole here. Decide which direction you want to work. Let's say you're starting from here with a
positive charge.
A hole.
Yes.
Okay? So potential-wise, it makes sense, right? But once the hole comes here, it has to remove an electron from the acceptor band, right? And where will it go?
Back to where it came from.
And that costs energy. So just considering the potential ignores this part. So I'm putting back this part by demanding this constraint. And basically, what do I know at the end of the day? The delta phi will, at the end of the day, depend on the difference in energy between those two states. Right? That's a game that we play here. We're in steady state at the end of the day. So moving one direction or the other direction must be equal. But in one direction you are changing the potential energy. In the other direction you are changing the energy of the states that you occupy. And when I'm writing just this, I'm forgetting about the second part, so I'm putting it back. Why do I do this whole game? Because the levels of acceptors, the levels of donors, the number of acceptors, the number of donors can't be manipulated easily, right? I can't take my PN junction, my diode, and change the number of acceptors. Well, I can, but that's a whole procedure. I'll have to stick it into an oven, put it in a reactive gas of donors, wait till they'll diffuse into it. A whole complicated structure. Potential, I change very easily, connected to a battery. So therefore, I want to concentrate on what the potential does without going into all the other details, and that's what I'm doing here. So, once I understand this point, which springs out of these two equations, because at v equals 0 they must be equal, then I can understand what applying a voltage on this diode will do. And first of all, before I go into a deeper analysis, what do you see here? What is this function? Dependence on V. All these are constant, right? They don't depend on V, they depend on the internal properties of the PN junction. So, what is the dependence on V? exponential. So it's very non-ohmic. Ohm's law tells you that I depends on V over resistance, where resistance is a constant. A simple linear dependence. This is the almost the furthest that you can move from a linear dependence. It's an exponential dependence. And conceptually what happens, I can't manipulate this, but I can manipulate this guy. And since the question is moving up in energy is always an exponential dependent procedure, voltage has an exponential influence here on the current. And now, now we'll take a break, and after the break, understand why putting in V in one direction will have a very little influence on the current. Putting V in the other direction has an exponential difference in current. An exponential effect on the current is basically an amplifier. Something that I do a small change in potential but get a great change in current, that's an amplifier. I take a small voltage and turn it into a huge current. And that's one part of the game, and the other part is that it's very dependent on the direction. In one direction it has a strong influence on the current, and we'll see it on the other direction it has a very small influence on the current. So we'll stop for a quarter of an hour and be back in 15 minutes or so.
近似连续，它比较密，也不是完全连续，因为可以近似连续，然后用费米黄金法则就认为它是连续的就行。对，是连续。然后它是个费米黄金法则，所以采越拧到自由电子系统，就是越相当于越强的连续。休息多长时间？15分钟。小牛妈呀！我说一句，妈呀，拼姐还是他妈的回听摇反掌，他妈的没摇反掌的好是吧？没摇反掌的好，好是拼姐，我无语了。哎呀！加位的时候，正位的时候，它会变高呀，完全讲反了吧？这他妈的，这后面偏解属于正向偏置 ，P 大于 n 的电压是他妈势力会减小呀！妈的，怎么成红的了加正的？完全讲反了吧？它
确实势力会减小，变成绿的。
就变成绿的，那为 讲反了吧？我感觉完全讲全是反的，而且他那个定义 generation current recombination 完全都是反的呢。啊？啊？操，什么鬼啊？不是，它这个 recombination current 结合的不应该是它扩散结合的扩散结合从 P 到 N 是没什么问题，因为他妈的电子是自由移动，自由移动电子从这儿，空缺是从 P 到 N 的。最后结合的跟产生的肯定是 N 到 P， 因为 N 到 P 会逐渐产生一个，但是电势画的不对吧？
它这个势不只是电势吧？
就它外加的电势化从 P 到 N 的话，它应该是减小啊，因为这个德尔塔负 i 是从 N 到 P 的负 i， 这个负 i 是从 N 到 P 的负 i，
左边是 P， 右边是
N 到 P 的负 i 应该是，
这个 phi 不只是电势，它是加了电势之后的总势的一个，它是加上了扩散势和电势一块的一个势吧？
没有，刚开始没有电势，它就是一个扩散势。刚开始没有电势，所以是负 i， 然后
后来又加了一个电势。
对呀，所以加电势的话，它加那个红的是从 P 到 N 的电势，还是从 N 到 P 的电势啊？红的
是电子到 N 到 P， 还是正电子，还是正电？
空穴，它电流加了位之后外加的，就是电流是 P 到 N， 电子是从 N 到 P 的。
对啊。
所以它这成了加了电子从 N 到 P 的，照它这个理论的话，电子从 N 到 P 他妈势力会变高了。比如说你给 P N 结加个他妈正向电压，他妈成了他妈势力变高了，势力越来越高了，哥。对吧？我查的是 P N 结除以正向偏置，也就是说 P 项加上正电荷。
你看它后面说的这个 recombination current 是正比于这个减位的，不是正比于正位的，不是正比于加位的。正向的它弄了个减位这里。
对，正向它弄个减位的，我不明白为什么正向会减位，但是我查的这个资料上，就是 P N 结加正向电压的时候，它的势力会减小。
对啊，所以应该就是这个图有问题，这个式子没问题。这个式子上还是减位的，就是势力减小的。
但为什么它正位要画个加呀？我操！
它一会儿电子，一会儿正电子。
哦，有人说这个负位其实是表现出正位的东西来，是吧？但也不对，它最后一个式子写的位如果是正的话，下边的 recombination current 大于 generation current， 这不就是势力增加吗？比如说位，这个位其实是这个位其实是负位，比如说可以理解为这个位其实是添加的，在这个表现形式上是相当于添加反向偏置，这个位这个表现上。
因为这个位带符号吗？
对，这个位其实是负的。只能这么解释，要不然不对。你只有这个位是负的话，加正向电压的话，是从 P 到 N 的话，它的 recombination 才会小于 generation， 然后才能有一个很高的电压，就肯定是 recombination 内电场肯定要小于外电场，那内电场能大于外电场，那在开玩笑呢？内电场只有小于外电场的势力才会减小呢。
recombination 应该是随着
内电场
而减小的。
对 recombination 应该随电压加正向电压会减小的。
所以这个减位的话，应该是相当于把德尔塔 phi 增加了，所以位应该是负的这个式子里头。
我操，他为什么势力会他妈的？也不对，他妈的。不是，他这个 generation current 应该是势雷吧？
它就是产生空穴电子对儿的这个 generation 是指的是 generate 空穴电子对儿。
generation 变小，好像没什么问题。E 变大的时候 generation 会变小。E 加正向 generation 会变小。唉，那从哪买的？
动画链接。
哦。先掏什么？
嗯。
这在讲什么牛马呀？
不知
知道，听不懂。
能不能把那本书借我看？上面有。
不知道。
查查，叫什么牛马呀？
加正向电压这个左右的 dp 点 dn 确实是减小的吧？
加上电压是减小，对。
对啊，它是增加这个减小，我感觉好像是一个。
不，是雷，他说是是雷，他现在就是雷，应该是绿的线，加正向电压是绿，加正向电压应该是绿的线吧？
不是加正向电压之后，它中间这个间就会减小，它绿的这个是增大的话的。